And it looks like we are live. Go ahead and share this out. All the information is correct. And we're good. Okay, so you up there. There. Okay, and I don't need you playing. So let's go take a look at where we are today. Last time we finished the minigrep project. One thing that I do realize is that we never actually built that project for production. But I mean, we did go through it and like complete it. It's just the book didn't actually have us build it out, which is a little bit interesting. Let's go for learning Rust. That's where we are, and currently at functional language features, iterators, and closures. So I mean, we're definitely so into chapter 13 now. It feels a little bit odd that we didn't switch to like do anything with production wise. Let's see, still got a little bit of the fuzz going on. I think that might be because yesterday I was able to not have that, but it also was a afternoon stream. So there's a little bit more light coming through the windows, maybe. Put a dark mode on this. It's a little bit easier to see. Let's one that too. Okay, but regardless, let's go ahead and get everything else set up. Or specifically, like oh yeah, we're gonna go over that kind of stuff. I'll get this set up as soon as we need to go into it. Until then, let's just begin. So, functional language features, iterators, and closures. Rust design has taken inspiration from many existing languages and techniques, and one significant influence is functional programming. Programming in a functional style often includes using functions as values by passing them in arguments, returning them from other functions, assigning them to variables for later execution, and so forth. In this chapter, we won't debate the issue of what functional programming is or isn't, but we'll instead discuss some features of Rust that are similar to features in many languages often referred to as functional. More specifically, we'll cover closures, a function-like construct that you can store in a variable. Some people also call them Lambda functions. They're basically anonymous functions. They don't ever get the name, they just exist right there. Iterators, a way of processing a series of elements. How to use these two features to improve the I/O project in Chapter 12. The performance of these two features, spoiler alert, they're faster than you might think. Other Rust features such as pattern matching and enums, which we've covered in other chapters, are influenced by the functional style as well. Mastering closures and iterators is an important part of writing idiomatic, fast Rust code, so we'll devote this entire chapter to them. A thing about closures, specifically used for these callback functions that we've seen here. It is a super powerful thing that can be done because we could define them in different places. One thing that I'm really curious about is, can a closure be set inside of like in a variable? Can we assign it to a variable? And I don't think that we can, but I think if we do repl.it and we go to Rust, Nope, I don't want to sign up. Just give me Rust. It's thinking. Okay, so we have our main RS. I mean, could I do something like let my function equals, and then just say, hey, we're taking in a variable a, and we're going to return a plus 1. Like, is that something that we can do? And because I don't think that we can do that in Rust. I think that it could only be like, hey, we're taking in a function here, because this is not really a type. Unable to infer enough information about underscore type annotation or generic parameter binding required. So that wasn't quite the same error message that I was expecting. I was expecting it just to say no. I don't know how to take it in. I don't know how to write a function on its own that does it. We could write a vector really quickly. So that numbers equals back of like 1, 2, 4. And then we could say let new numbers equals numbers dot map, and then this one will take my function, and then we want to print line new numbers. This work? No method name map found for type, standard vector in the current scope. Oh, I keep on, okay. Rust vector map. Oh, it's like an iterator map. Into iter, and then I can map. That's what it is. Into iter, and then map. Dot into iter, and then we can map. The trait bound map is not satisfied. Interesting, for new numbers. Interesting. It is showing me the trait bound standard vec into iterator debug is not satisfied. In this expansion, okay, is there any more? Reverse.collect to go back into it. So collect to get back into a vector. Unable to infer enough type information about, okay, so I don't think I can sort of force to do it, but I might be able to. It's not telling me I directly can't. It's like going around it. It's not really getting into the map as the problem. It's getting into this other thing. But that's for another time. Let's just continue on and not get too sucked down into that. Closures, anonymous functions that can capture their environment. Rust closures are anonymous functions you can save in a variable. So you can save the functions in a variable, or pass as arguments to other functions. You can create the closures in one place and then call the closure to evaluate it in a different context. Unlike functions, closures can capture values from the scope in which they're called. We'll demonstrate how these closure features allow for code reuse and behavior customizations. Creating an abstraction of behavior with closures. Let's work on an example of a situation in which it's useful to store a closure to be executed later. Along the way, we'll talk about the syntax of closures, type inference, and traits. Consider this hypothetical situation. We work at a startup that's making an app to generate custom exercise workout plans. The backend is written in Rust, and the algorithm that generates the workout plan takes into account many factors, such as the app user's age, mass, body mass index, exercise preferences, recent workouts, and an intensity number they specify. The actual algorithm used isn't important in this example. What's important is that this calculation takes a few seconds. We want to call this algorithm only when we need to, and only call it once so we don't make the user wait more than necessary. We'll simulate calling this hypothetical algorithm with the function simulated expensive calculation, shown in listing 13-1, which will print calculating slowly, wait for 2 seconds, and then return whatever number we passed in. So, name main source. Interesting. So then they have the sleep here. Oh, thread sleep. Interesting. So they're having sleep wait in a thread, but then we're waiting for that. And then it returns whatever is passed into it. Let's play with this. So we're gonna open up our terminal. So we'll go to learning Rust. We have to now create chapter 13. And inside of here, let's go ahead and create cargo new, we'll call this closures. And open up code here. Okay, so we've got our basic main RS here. Let's go ahead and recreate the function they have here for us, which is the most interesting thing is that we're using thread and we're using center time duration. Then other than that, it's just really using these. So center thread, center time duration. Use standard thread, use standard time duration. Then we want to create a function. So function long calculation. And this takes in a number. So it takes in a result, which is a, I think they said like it was a U32. Yep, intensity, which is U32. That one. And we're gonna return a U32. And then we're going to do our print, which is waiting for a long time. So print line. I don't really need any of that here. I could just say waiting for a really long time. And then we're gonna thread sleep it. So thread sleep, and duration would be, is it 2000? It's 2. Oh, duration from sex. Thread duration. Hold on, I want to do that. Thread sleep duration from seconds. Okay, got it. So thread sleep duration from seconds 2. So we're gonna initiate a thread, and then we're just gonna return at the end the intensity. Then of course this isn't being used, so what we can just immediately do is run long calculation and pass it 42. And let's go ahead and run this and see it pause for us. So cargo run, cargo run. And so it does exactly what we thought it would do. Okay. Next is the main function, which contains the parts of the workout app important for this example. This function represents the code that the app will call when a user asks for a workout plan. Because the interaction with the app's front end isn't relevant to the use of closures, we'll hard code values representing inputs to our program and print the outputs. The required inputs are these: an intensity number from the user, which is specified when they request a workout to indicate whether they want a low intensity workout or a high intensity workout. A random number that will generate some variety in the workout plans. The output will be the recommended workout plan. Listing 13.2 shows the main function we'll use. So simulated user specific value is 10, simulated random number is 7, generate workout, and then we call generate workout and we pass in the two things. So simulated intensity equals 10. Oh, and I forgot the let simulated random equals 7. Then we're going to pass it, we're going to call long calculation, and they want us to do it in this way: simulated intensity, simulated random. That, of course, will cause an error because this function doesn't take that in. So now we need to like update the function to handle this, because right now, yeah, this is not even like a tuple or something that they're passing in. So this just doesn't work. We've hard-coded the variable simulated user specified value as 10 and the variable simulated random number as 7 for simplicity's sake. In an actual program, we'd get the intensity number from the app front end, and we use the rand crate to generate a random number, as we did in the guessing game example in Chapter 2. The main function calls a generate workout function with the simulated input values. Now that we have the context, let's get to the algorithm. The function generate workout in listing 13.3 contains the business logic of the app that we're most concerned with in this example. The rest of the code changes in this example will be made to this function. Okay, so now we're going to update this, so we take intensity and then the random number. So, oh, now we have a generated workout. Okay, so now we're going to create a generated workout that takes the intensity and the number. So this is not long calculation. This is generated out. Of course, doesn't exist yet, so we need to create that. So function generated workout, and you're going to take in intensity, which is a U32, and a random, which is a U2. And what are we going to return? Nothing at all. Super awesome. So if intensity is less than 25, we do X push-ups. X do X sit-ups. Else, if random number equals 3. Okay, that's very interesting. Take a break today. Remember to stay hydrated. Okay, so if the intensity is less than 25. So, if intensity is less than 25, then we want to do X push-ups from the simulated expensive calculation. Okay, so print line, do push-ups, and we're going to call the long calculation. I'm going to pass in the intensity. Also, I don't need U open. So that's for that one, and then we also want to do X sit-ups. So we're just going to do the exact same number of push-ups and sit-ups. And line, sit-ups, long calculation, and pass in intensity. Perfectly fine. Then coming down here, we have our else condition for this intensity, and then we check if the random number is 3, which it is not because we set it to 7. Then we're going to do these things, which doesn't seem to make any sense because we're not actually going to run those, but we might be changing a number. So let's just run it anyways. So else, if the random number is 3, then we have this else. So if random equals 3, then what are we going to do here? Print the line, take a break today. So line, take a break today. Otherwise, we're going to run for X minutes. Print line, go run for minutes. And this will be our long calculation with intensity. Okay, so this should actually work now. If I run this, it should give us some stuff. Do 10 push-ups, do 10 sit-ups. Perfect. The code in listing 13.3 has multiple calls to the slow calculation function. The first if block calls simulated expensive calculation twice. The if inside the outer else doesn't call it at all, and the code inside the second else calls it once. The desired behavior of the generate workout function is to check whether the user wants a low intensity workout indicated by a number less than 25 or a high intensity workout, a number of 25 or greater. Low intensity workout plans will recommend a number of push-ups and sit-ups based on the complex algorithm we're simulating. If the user wants a high intensity workout, there's some additional logic. If the value of the random number generator by the app happens to be 3, the app will recommend a break and hydration. If not, the user will get a number of minutes of running based on the complex algorithm. This code works the way the business wants it to for now. But let's say the data science team decides that we need to make some changes to the way we call the simulated expensive calculation function in the future. To simplify the update when those changes happen, we want to refactor this code so it calls the simulated expensive calculation function only once. We also want to cut the place where we're currently unnecessarily calling the function twice without adding any other calls to that function in the process. That is, we don't want to call it if the result isn't needed, and we still want to call it only once. Refactoring using functions. We could restructure the workout program in many ways. First, we'll try to extract the duplicated call to the simulated expensive calculation function into a variable as shown in listing 13.4. So let expensive result equals this, and then we just use that outside. So that's easy enough. We come into here, and inside of our long calculation, we print line, but we can actually it's generate workout in here. We can say let workout number equals long calculation. We pass it the intensity, and then in here, we're going to replace everywhere where we have long calculation except for that one. We're going to replace that with workout number, which should still now work. This should still work perfectly the way we want it to. This change unifies all the calls to simulated expensive calculation and solves the problem of the first if block unnecessarily calling a function twice. Unfortunately, we're now calling this function and waiting for the result in all cases, which includes the inner if block that doesn't need to use the result value at all. We want to define code in one place in our program, but only execute that code where we actually need the result. This is a use case for closures. Refactoring with closures to store code. Instead of always calling the simulated expensive calculation function before the if blocks, we can define a closure and store the closure in a variable rather than storing the result of the function call, as shown in listing 13.5. We can actually move the whole body of simulated expensive calculation within the closure we're introducing here. So what we have is let expensive closure equals, it takes in a number, and the body of it is print that, do the thread, and then we return the. Okay, let's do that. Then we can call this whatever we want. So generated workout is now going to be a closure for us. So where would we want to put this? Probably, I wonder if I can define this down here, or if we want to like pass it through. So let generated workout, oh wait, sorry, wrong one. Let long calculation equals, and we're going to bring in intensity. Now I can't remember, do we have, it's just a number, so we can't deal with like U32 or anything. This is really just going to be intensity here. We're not going to say what we're going to return. Instead, it's just, okay, we're going to close with here. All of this stuff is the same, and then we return the intensity. And then we close with a expected item found let. Does this need to be in the main function? Where are they putting this? I guess they don't tell us yet. But it's not happy with us putting it here, just outside. We're either going to have it in main, and then it will be available in the scope, or we're going to put this inside of here. And now we can use this. Yeah, so it's much happier with that. So that workout number equals this. We don't want to do the calculation right now. We would want to do it here. We're going to call long calculation and pass it the intensity. Cargo run. Although that doesn't seem to solve the problem, so I'm curious about how that's going to work. The closure definition comes after the equal sign to assign it to the variable expensive closure. To define a closure, we start with a pair of vertical pipes, inside which we specify the parameters to the closure. This syntax was chosen because of its similarity to closure definitions in Smalltalk and Ruby. This closure has one parameter named num. If we had more than one parameter, we would separate them with commas, like param1 and param2. After the parameters, we place curly brackets that hold the body of the closure. These are optional if the closure body is a single expression. The end of the closure, after the curly brackets, needs a semicolon to complete the let statement. The value returned from the last line in the closure body, num, will be the value returned from the closure when it's called, because that line doesn't end in a semicolon, just like in function bodies. Note that this let statement means expensive closure contains the definition of an anonymous function, not the resulting value of calling the anonymous function. Recall that we're using a closure because we want to define the code to call at one point, store that code, and call it at a later point. The code we want to call is now stored in expensive closure. With the closure defined, we can call the code in the if blocks to call the closure to execute the code and get the resulting value. We call closure like we do a function. We specify the variable name that holds the closure definition and follow it with parentheses containing the argument values we want to use, as shown in listing 13.6. So it's the same, but it's the same problem now. So we see this. Now the expensive calculation is called in only one place. Here. And we're only executing that code where we need the results. However, we've reintroduced one of the problems from listing 13.3. We're still calling the closure twice in a first if block, which will call the expensive code twice and make the user wait twice as long as they need to. We could fix this problem by creating a variable local to that if block to hold the result of calling the closure. But closures provide us with another solution. We'll talk about that solution in a bit, but first let's talk about why there aren't type annotations in a closure definition and the traits involved with closures. I wonder if closures can allow us to cache. Closure type inference and annotation. Closures don't require you to annotate the types of the parameters or the return value like FN functions do. Type annotations are required on functions because they're part of an explicit interface exposed to your users. Defining this interface rigidly is important for ensuring that everyone agrees on what types of values a function uses and returns. But closures aren't used in an exposed interface like this. They're stored in variables and used without naming them and exposing them for users of our library. Closures are usually short and relevant only within a narrow context rather than in any arbitrary scenario. Within these limited contexts, the compiler is reliably able to infer the types of the parameters and the return type, similar to how it's able to infer the types of most variables. Making programmers annotate the types in these small anonymous functions would be annoying and largely redundant with the information the compiler already has available. As with variables, we can add type annotations if we want to increase explicitness and clarity at the cost of being more verbose than is strictly necessary. Annotating the types for the closure we define in listing 13.5 would look like the definition shown in listing 13.7. I wonder if, does that mean that closures don't need to be created as generics, like they are generic and they can be used in multiple ways? I'm curious about that now. With type annotations added, the syntax of closures looks more similar to the syntax of functions. The following is a vertical comparison of the syntax for the definition of a function that adds one to its parameter and a closure that has the same behavior. We've added some spaces to line up the relevant parts. This illustrates how closure syntax is similar to function syntax, except for the use of pipes and the amount of syntax that is optional. Yeah, the body, if it's one line, the block is unnecessary. These could be very short. The first line shows a function definition, and the second line shows a fully annotated closure definition. The third line removes the type annotations from the closure definition, and the fourth line removes the brackets, which are optional because the closure body has only one expression. These are all valid definitions that will produce the same behavior when they're called. Closure definitions will have one concrete type inferred for each of their parameters and for their return value. For instance, listing 13.8 shows the definition of a short closure that just returns the value it receives as the parameter. This closure isn't very useful except for the purpose of this example. Note that we haven't added any type annotations to the definition. If we then try to call the closure twice, using a string as an argument the first time and a U32 the second time, we'll get an error. So we would have to create generics for it. Okay, that makes more sense. The first time we call example closure with the string value, the compiler infers the type of X and return type of the closure to be string. Those types are then locked into the closure and example closure, and we get a type error if we try to use a different type with the same closure. Storing closures using generic parameters and the function traits. Let's return to a workout generation app. In listing 13.6, our code was still calling the expensive calculation closure more times than it needed to. One option to solve this issue is to save the result of the expensive closure in a variable for reuse and use the variable in each place we need the result, instead of calling the closure again. However, this method could result in a lot of repeated code. I wonder, does this closure exist, like continue existing? Like, for example, could I say if intensity equals, and what are we passing in? Simulate intensity 10. It is that one. So I would need, like, I'm not exactly sure the best way to like do a storage in this way, because it's like not normal. If cached because I don't want to say like let cached either. Yeah, I'm not sure the best way to do like any kind of caching in there, but maybe they'll tell us how to do that. Fortunately, another solution is available to us. We can create a structure that will hold the closure and the resulting value of calling the closure. The struct will execute the closure only if we need the resulting value, and it will cache the resulting value, so the rest of our code doesn't have to be responsible for saving and reusing the result. You may know this pattern as memoization or lazy evaluation. To make a struct that holds a closure, we need to specify the type of the closure, because a struct definition needs to know the types of each of its fields. Each closure instance has its own unique anonymous type. That is, even if two closures have the same signature, their types are still considered different. To define structs, enums, or function parameters that use closures, we use generics and trait bounds, as we discussed in Chapter 10. The function traits are provided in the standard library. All closures implement at least one of the traits, function, fnmute, or fnonce. We'll discuss the difference between these traits in the capturing the environment with closure section. In this example, we can use the fn trait. So, fn trait, interesting. We add types to the fn trait, bound to represent the types of the parameters and return values the closures must have to match this trait bound. In this case, our closure has a parameter of type U32 and returns U32. The trait bound we specify is fn U32 returning U32. Listing 13.9 shows the definition of the cacher struct that holds a closure and an optional result value. So the callback isn't itself sort of like cached and kept in memory, so that way it can like keep variables that live. Instead, we just use structures to sort of wrap around it. So I wouldn't necessarily call that a feature of the people want to say like anonymous functions or lambdas of these closures. It's just more of a feature of structures that allow us to do that. So you have a struct cacher of anonymous t or generic type where t is function u32. So then we set the traits. We limit the traits to where it's types functions. Okay. And then calculation t, value option u32. Interesting. Okay, so let's create the struct cacher. So we'll do that up here. And this is type t, where, and this or t is this. T fn u32. And this is going to return a u32. I need no semicolon needed for this one. Where t, it's upset with this right now, but it's probably expected identifier count where, oh, that's because this needs to go above here. And then we have these in here where we say like, hey, it's not actually doing that for us yet. Now we can have calculation t. Calculation t, and also the value option. So an option enum, which takes in a u32. So where f and capital F. And then it's never used. So perfect. So how would we use this? Can I guess? So in our generated workout, we need to, for cacher and generated workout, we need to store the function inside of here. So we can have let long calculation, or we're really going to also then say let maybe it's going to be this. That long calculation is going to be cacher, which is then going to take a calculation, which is this entire thing. So intensity, let's tab this in, also. And then we also have a value which is not set to anything. Can I get away with that? I expected one of, semicolon. Missing field value in initializer of cacher. Missing value is the value. Okay, so no, the answer is no, I cannot do that. So I have to have a value here. And can I just say none to initialize it? Yeah, it looks like I can. So because it's an option, okay, so we're using option because we want to be able to say, hey, it's none here, which is like the equivalent of null. So then we have our long calculation. The thing with this, I'm guessing we're going to have some implementations here. So we would have to like implement cacher, where we have a function calculate. And this is going to take in a reference to self. So it's to self. And it's going to take in our intensity, which is a U32. And we're going to return a U32. So what are we going to do here? We're going to say, okay, if the value, we could match on self value, or we can attempt to unwrap it. I think we should match. Okay, so we can match on the self.value. And what this will be is it's an option, right? So we're either going to have a sum of a number, and if it's some number, then we're fine. We just pass this number. Otherwise, we get a it's a none. And if it's none, then we want to run the calculation and assign it to the value, which probably means this needs to be mutatable, but we'll run into that in a second. So none is going to be a we run the calculation. So we're going to put into value, so self dot value equals, this is going to have to be block here, self dot value equals run the calculation, self dot calculation. We're going to hand it the intensity. And what else do I care about right here? I don't think anything. This is inside of a block, so it needs semicolons. And then we want to return the self.value. That returns out like that. Wrong number, type of arguments, expected 1, found 0. Oh, so for implement, I also need to then set t here. I'm gonna find type t in a scope. I need to remember how to do those. But I think I'm on the right path, and let's find out if the book catches up with us and where we want to be. The cacher struct has a calculation field of the generic type t. The trait bounds on t specify that it's a closure by using the function trait. Any closure we want to store in a calculation field must have one U32 parameter specified with the parentheses after fn and must return a U32 specified after the thin arrow. Note, functions implement all three of the fn traits too. If what we want to do doesn't require capturing a value from the environment, we can use a function rather than a closure where we need something that implements an fn trait. The value field is of type option U32. Before we execute the closure, value will be none. When code using the cacher asks for the result of the closure, the cacher will execute the closure at that time and store the result within a sum variant in the value field. Then, if the code asks for the result of the closure again, instead of executing the closure again, the cacher will return the result held in the sum variant. The logic around the value field we've just described is defined in listing 1310. So implement t cacher t. Okay, so that's what we needed. So it's right here. Implement t cacher t. The trait bound t is not satisfied. The trait standard ops function U32 is not implemented for t. Consider adding a where t. Can I just like copy this? Bound. Okay, so we'll copy that and put it right before here. The precise format of function family traits type parameters is subject to change. Use parenthetical notation. Function foobar baz. Oh, I probably want to do this type. So they told me to do this and it was wrong. We want to do function 32, 32, like that. U32. All right. So then inside of our function, mismatch types. So self.value, not a U32. Self.calculations, no method name calculation found for type, but it's right here. No method name calculation found for type cacher, generic T in the current scope, field not a method. Help use self-calculation if you meant to call the function stored in the calculation field. Oh, interesting. Okay, so I need to wrap these in parentheses and then I can call this parenthesis here. That's interesting. So if we do that, expected enum standard option found U32. So now inside of here, we need to return a sum or value. I could actually just do sum this and like that. Yes, okay. And then self.value expected U32 found enum. So now I want to unwrap like that. All right, and now it's working. So long calculation is not being executed now, or it's not properly. So we want to do long calculation dot calculate is what we really want to do. It's going to be long calculation dot calculate and pass it in the intensity. And I don't see any error. Oh, I see an error here. Cannot assign to field self-value of immutable binding. So we need to say that this value is mutable, which means we also need, let's see, self.value, no field value on type cacher. Expected identifier. So I can't put mutable there. Struct, put it here. No, definitely not there also. Where do I put the mutable again? Or is it here? No, that doesn't make any sense. Or is it just a reference, a mutable reference to self? Expected identifier found. Finally, that's the last. Okay, that works. So we get a mutable identifier to self. We don't need to change anything there. Let's see if this works any better. Cannot borrow immutable local variable long calculation as immutable. Oh, so I want to borrow only one of the things in there, but not both. Cannot borrow mutably. Wait, what am I doing mutably here? Let long calculation equals. Oh, I need to tell it down here to be mutable because we're mutating it up here. Interesting. Okay. Let's try that. and then it works. So the caching system is set up for us. Let's see what else we need. Well, we're getting close. So let's power through this section. We want the cacher to manage the struct's fields values rather than letting the calling code potentially change the values in these fields directly. These fields are private. So we have this. The logic around is described here. Implement t, cacher t, where t is this. Function new calculation. So function new. Oh, you know what? They had a new here, which we didn't add in the new section for it to make it more Rust-like. I think that's the key. Is like I keep on forgetting that that's a thing that we do, and I think that's what we're going to do next time, which is change implement of cacher to be new. Let's go ahead and update our README really quickly. Vim README. So currently at this, I think I also want to change this to be listing 1330. As I'll just copy. No, back. Okay, I'll find it. Or is this it? Function new. Okay, I think this is. So here we are, listing 1330. But specifically, what we're doing here is we're updating implement to create new instance of cacher instead of having the code do it. Okay, so perfect for that. Then we have u. We want to change u down. Currently we're at, I don't actually know the best way to get here, so let's just go to this close one. Okay, we'll save that. Let's go and push our code up to GitHub so we don't forget that. And we're saying all about closures and caching. And sending on up to GitHub. So all of this code I have linked to in the stream description or in the YouTube VOD description. And that's up here on my Learning Rust GitHub repo. You're gonna see chapter 13 closures are here now. I'm doing these Learning Rust, reading through the book streams every single weekday morning at 7 a.m. Mountain Time. I'll be back tomorrow morning for that. We end around, we do this for around 1 hour, so we are just finishing up right now. Thank you everybody for stopping by and taking a look. We had a couple people today, and it looks like we're going to continue on with the closures tomorrow with chapter 13. And then moving on. If you would like to follow me to get notifications of when I go live, please follow me here on Twitch, or you could also follow me on YouTube to get the notifications when I upload archived videos of these streams. You can also find me on Twitter, where I tweet out when I'm going live as well. Sometimes I do unannounced, like unscheduled streams. I did one yesterday for just working through Coding Game with West. With that, I'm going to go get ready for the rest of my day, and I hope that you have a great one as well. See you tomorrow.